All right, guys, welcome. So here's another episode of Math with Marty. In the last video, I talked about an intro to parabolas. So I introduced, the base curve and different quadratics and how to plot them using a table of values. I introduced the idea of the vertex. I introduced the idea of the axis symmetry and things like that, x-intercepts. Now, the simplest quadratic that we can plot and that we did plot in the last note was y equals x squared. Y equals x squared is called the base curve. This is the base curve of the quadratic relation. Now, in order to plot this, we first need its vertex. So, step one is to get the vertex. So how do we get that? Well, this is in vertex form, and to get the vertex, here's what you do. You have to ask yourself, is there a bracket around the x term? There is no bracket at all. What that implies is that the x-coordinate of the vertex is 0. Then to get the y-coordinate of the vertex, you need to ask yourself, what is the coordinate to the right of the exponent 2? There is no number. Therefore, the vertex is 0. So there's your vertex. The vertex on a parabola is that point right at the bottom. So that point is the vertex of your parabola. Now, it is also, therefore, in the middle of the parabola. So what I'm going to do is I'm going to build a table with that vertex in the very middle. So I'm going to write out x, y, and 0, 0 is going to be in the very middle of the table. Now, obviously, if I want to plot a parabola, I need way more points. I need more points on that actual function. So I'm going to go backward from 0, and I'm going to go forward from 0. To go backward from 0, I get -1, and I'm going to get -2. To go forward, I get 1, and I get 2. Now, if you notice, there's some y values here that are missing. How do I get them? Well, I plug in those x values into this equation. You see, this equation tells me that if I square x, I'm going to get y. So what is the square of -2? The square of -2 is +4. So I end up getting +4 here. And the square of -1 is 1. Now, since 0, 0 is in the middle, I bet the next two values are going to be 1 and 4 because the parabola has to be symmetrical. It has to have the same y values. Let's double check. What is 1 squared? Well, 1 squared is 1, and 2 squared is 4. So right away, I know I'm correct. I've got some symmetry here. 0 is in the middle. Okay, so that is a review of how to plot y equals x squared. Now I'm going to show you a perfect drawing of y equals x squared as through Desmos. So I've got these points in blue, and those points are on the y equals x squared curve. So this red curve is y equals x squared, and these blue dots are the 5 points that I have in that table. So this is the simplest parabola that I can actually draw. So how do we complicate things a bit? Let's investigate. So it's time to complicate things. I've got my y equals x squared, and what I'm going to do is I'm going to introduce a number. I'm going to choose it at random. That number is 2. So I got to ask myself, what does this 2 do? Well, if I were to plot this, what would it look like? Let's plot y equals 2x squared. So the purple or blue curve is y equals 2x squared, and y equals x squared, the original, is in red. How has the red curve changed? If you notice, the blue curve is actually thinner than the red curve. So by introducing this 2 right here in front of x squared, I've made my original curve thinner. It has basically stretched upward my red curve to produce the blue. Every single y value has been modified. So for example, I have 2, 4 in my red curve, but in my blue curve, it is 2, 8. Every y value is doubled. Now, of course, if I double 0, 0, it's not going to change. 2 times 0 is still 0. So that's why my vertex hasn't changed. What about 1, 1? How has that changed? So 1, 1 on the red curve is now 1, 2 on the purple or blue. So what that transformation does is it basically multiplies all the y values by 2, all the original ones anyway. And so it's been stretched up. And that can also be said for other values, so long as they satisfy the following criteria, that they are bigger than 1. So for example, y equals 3 also does the same effect. Y equals 4, y equals 5, 6, 7, 8, 9, 10. And let's make it dramatic. Y equals 100. What this means is that if you make that a value, I'm going to call it the a value, if you make that a value more and more massive, if you make it larger and larger, then the curve gets stretched more and more and more and more. It gets thinner and thinner every time. So this a value causes a vertical stretch and in this case it's by a factor of 2. I can abbreviate this as Vs by a factor of 2. Now some teachers want you to say by a factor because it means a multiplicative factor, but for my sake I'm just going to write by 2. Okay? So that's for values that are bigger than 1. What about values that are smaller than 1? So for example, if I have decimal values, what if I had, instead of something as dramatic as 100, what if I had 0.5? See, that's a decimal that's smaller than 1. What happens? Well, the opposite happens. Before, the blue curve was above the red. It was a vertical stretch. What happens now? Well, if you notice, the blue curve is actually below the red. You see, the red had a 0.24 on it, and now the blue has a 0.22. The y value has changed, the x value did not. See, now instead of multiplying all the y values by 2, you actually multiply all the y values by 0.5. So instead of having a curve that's narrower, like before, it is now wider. The curve has basically, instead of been stretched upward, it has been compressed downward. Someone took the ends of the parabola and pushed down, causing a flatter curve. And I don't have to stop at 0.5. I could have done 0.8, and the blue is still below the red. I could have done 0.2, and the blue is still below the red. 0.1. I could have done something as dramatic as 0.01, and the blue is very much compressed. You see, so long as the decimal is less than 1, you get a compression. That's the rule. So let's bring it back to 0.1 to not be so dramatic about this. So you have an example like this. So you've got y equals, we're going to do this one in blue, 0.5 x squared. See, this is not a vertical stretch by 2. No, this is a vertical compression by 0.5. So this, instead of being abbreviated VS, would be abbreviated VC. So these are two basic transformations that I can apply. Now, if you're familiar with integers, you know that I don't have to call it 2. Could I have included a negative? Let's say I made this 2 a negative. So instead of being 2, it would be negative 2x squared. What does that do? So let's go back. This was the 2x squared example that we just saw. What if I then put a negative sign? You see, what the negative does is it basically flips the entire parabola. It reflects it down. So another type of transformation that I can apply to my base curve, my original curve, is actually a reflection. So y equals x squared is the original. The second I introduce a negative to the left, what this negative does is it reflects the curve downward. It will face down. Instead of facing up with the arrow facing up, the curve will face down with the arrows facing down. So that's a second type of transformation. Let me do that in white. Okay. So I introduced a 2 right here in front. I introduced negatives. Let's try adding stuff over here. You see, I can have a transformation that looks like the following. So instead of multiplying by 2, in this case, what I'm doing is I'm adding 5. I can do that. But the question is, what does this do to my original base curve? Let's test it out. So the blue curve is the transformed curve. What has happened to my red curve? To produce the blue, what has happened is I've essentially lifted the entire curve up. You see, the old vertex was at 0, 0, and now the vertex is at 0, 5. Every single old y value has been added by 5. It has been increased by 5. So here I've got 1, 1, and over here I do not have 1, 1. I actually have 1, 6. 1, 6. So the old y value was a 1 in the red, but now it is a 6 in the blue. So basically, y equals x squared plus 5, we say vertically translates up 5 units. Translates just means shifts. It's a fancy math term. Vertically translates up 5 units. How would I abbreviate that? VT up 5. Who's to say I have to go up 5? Could I go down 5? The answer is yes, I can go down 5. How would I write that equation? That equation would be not plus 5, but minus 5. That would cause a VT down 5 units. So if I were to plot it, I should see the blue curve now all of a sudden below the red. And that's exactly what I have. Instead of having a vertex at 0, 0, the vertex is now at 0, -5, and the same can be said about every other y value. The old y value here was 1, and now it is at -4, because if you subtract 5 from 1, you get -4. So every single y value has been shifted down. Every single y value has been decreased by 5. That's what this does. What about this? What if I were to take that plus 5 and instead I were to put that plus 5 right beside x inside a bracket? And you know what? I'm going to do this in a different color. So what if I were to do this? Plus 5 inside the bracket. What does a plus 5 inside of a bracket do? Let's find out. Okay, a plus 5 inside of a bracket takes my original curve in red, and instead of moving it up or down, the plus 5 beside the x actually changes the x values this time. It shifts everything over to the left. You see, the vertex used to be 0, 0, but now the x-coordinate has been decreased by 5, and it is now at -5, 0. When that 5 is inside that bracket, it actually does the exact opposite to what you might think. Instead of adding to x, instead of adding 5 to x, it actually subtracts 5 from x to produce a new x-coordinate. So for example, this x-coordinate here was -1, but over here it is -6. The x-coordinate has been decreased by 5. This x-coordinate right here used to be 1, and now it is -4. It has been decreased by 5. So, if we go back to the note, what this does is it horizontally, horizontal just means along left or right, horizontally translates left 5 units. I abbreviate it by HT left 5. Who's to say I have to translate left, though? Can I go right? The answer is yes. All I have to do is switch that sign to a minus. And now, instead of the blue curve being over here, it is actually over here. So this is an example of a horizontal translation, right 5. So y equals x. I'm going to use red again. And this basically says HT right 5. So these are all transformations, again, done to y equals x squared. So these are all of the individual transformations that I can apply to y equals x squared. These are all simple one-step transformations. So for example, I've stretched, compressed, reflected, I've translated up, down, I've translated left, right. So what if I were to combine all of them into one expression? What if I were to take this 2 right here, let's say. What if I were to take that 2, that negative sign, this plus 5 on the outside, and this plus 5 on the inside, and I were to combine them into a single expression? What would that look like? Well, here's what I would get. I would get y equals -2 bracket x plus 5 squared plus 5. You see, this is called the vertex form of a quadratic relation. So the vertex form is essentially taking the original curve, the base curve, y equals x squared, and applying a series of transformations to it. That's basically what it is. So for example here, I've reflected the base curve down. Over here, I've vertically stretched it after reflecting down. Over here, I have shifted, or actually let's word it this way, ht left 5. Remember, you switch the sign inside the bracket. And over here, I have vt'd up 5, vertically translated up 5. So the negative means reflected down, the 2 in front means vertical stretch by 2, the 5 inside the bracket gets flipped and it goes ht left 5, and the 5 on the right side stays the same, but now instead of being left, it's actually an up, so it's a vt up 5. If this were a decimal, it'd be a vc. If this were negative, it'd be basically going right. And if this were minus on the right side, it would be actually going down. So let's graph this quadratic relation and see how it compares to the original. So the original is y equals x squared. The new curve is going to be negative 2 x plus 5 squared plus 5. Now I should expect to see a few things. I should expect to see that my blue curve is now reflected down, meaning it faces down. Does it face down? Absolutely. You see, this is a maximum curve, whereas here the red is a minimum curve, right? So now the blue faces down, thanks to that negative sign. Is my blue curve slightly thinner? Yes, it is. I can make it more thin if I want, if it's not apparent to you. Oops. So I changed the a value to a minus 50. Now it's slightly more thin. Let's stick back with the 2 though. It's still thinner. What does the plus 5 do? Well, it's supposed to shift it left. Is it left of the original vertex? It is, right? The blue vertex is over here, so it's been shifted left. Now, what has happened? It's also been shifted up because of that plus 5 on the end. So overall, the vertex has been shifted left and up. So my new vertex is at negative 5, 5 instead of the old 0, 0. So these are all the transformations combined. Everything checks out. Reflected down, slightly thinner, stretched up, shifted left, shifted up. And these are a summary of all the transformations that we've learned, and what we've generated out of it is basically vertex form. So I hope this video was informative. If you did enjoy it, leave a like, comment, subscribe. In the next video, I'm going to go more in depth into vertex form, and we're going to learn how to find an equation given some information. For example, if I give you the vertex, you should be able to somehow come up with a way to find the equation in vertex form. So I hope this video was good. I'll see you in the next one. Bye-bye.